That is full screen now. Is that right now? Okay, so I wanted to use Fruta del Norte as an example of the application of this model in a place where, you know, I'd had no previous experience. And so I just want to spend 20 minutes or so talking that through with you, sort of what we did. So I can't. Yeah, okay, thanks. Yeah, that's good. That changed. Yeah, so this is based on work that I did in 2007 to 2009, working for Aurelian and then Kinross. So this was just after the discovery in 2006, when Steve Leary's team, you know, made the discovery and then did the incredible exploration work that led to the resource definition in 18 months. And the job I had was to review the core to try and come up with a domain model that had already been done in part by Peter Stewart, but I looked at more holes and tried to expand that. In particular, I wanted to develop a more robust geological model for the ore controls. And so I started with the domain model, but then I took it further geologically. So you change slide. Okay, so I've a lot of this is from my own work, but I've added in particularly newer information from the Steve Leary economic geology paper and various other presentations that Carl Rower and Peter Stewart had done. But I've never really presented much on it because I wasn't part of that team ultimately. The main thing about Fruta del Norte is that it's hosted mainly in the Zamora batholith, which is the orange unit on there. Can I choose a pointer? Can you see my arrow okay? Oh, okay, sorry. Yeah. Yeah, so the orange stuff around the outside, that's the Zamora batholith. The darker orange in the middle there where your pointer just was, they're the volcanics that are in this graben. So those north northeast lines define the graben. You can see that more clearly in the right-hand close-up figure. And the green units there are the fill over those volcanics, the sediment fill over those volcanics. And the grey, I think, is the Hoyine. Oh no, that's the light grey is the Hoyine, which is unconformably over everything. In the right-hand diagram, the colours there, the purple in the middle, there, yes, and the red that's beside that, and the blue that's to the south of that, those are the domains that were originally defined mainly by Peter Stewart and I think are still being used to a fair degree now. So fundamentally, the ore body is elongate along the boundary of this pull apart basin in this graben. And it started when the graben was initiated, but as the graben, I think if you go to the next slide, yes, we can see it here. So the white hatch, the black and white hatch in the center right, that's the mineralization there, just to the right of that, just to the right, there. Yes. No, right there, yeah, that's where the ore body initiated. So you can see it's bound by one of the graben faults, and those faults are disrupting the volcanics in the intrusion, which is the darker orange and the pink unit there. So the basement, the existing rocks are being disrupted as this basin starts to develop, and then in the right-hand diagram, you can see as it develops, as the basin develops, the hydrothermal system extends up into the sedimentary rocks of the pull-apart basin, and where it says discovery outcrop, that is where Steve Leary first found mineralization. So it wasn't actually in the main part of the ore body, it was just a distal pile of sort of breccia with silica sulfide in it that reflected the underlying mineralization. But he thought that was enough to drill under that discovery outcrop, and when they drilled deeper they got into the units that you can see there. So the red thing, if you go down, the red horizontal thing there, just up between the white hatch and the green, the little bit of red there, yep. That's the sinter that formed its surface above the black and white hatch, which is a hydrothermal breccia pipe, and the veins that are the mineralization. Okay, so the ore body formed while the pull-apart basin was developing, and there are multiple phases of mineralization related to that. And this is important as we go forward. Go to the next slide. Okay, so here's the latest model that I've seen from London about the distribution of gold. You can see in the left-hand diagram, the overall, all the red there is, and purple and pink is the grade distribution, and the ore body is about 1,200 metres long and 300 metres wide. And in the right-hand diagram, which is an older one but says the same sort of thing, the mineralisation is about 300 metres deep. Okay. In the surface plan, the metallurgical domains are defined. The one on the left at the northern end is quartz. The one on the western side of that is chalcedony marcasite in the yellow, and then to the south is all the manganocarbonate. You see that in the plan and in the section. So these are the domains which are also relate to the textures and mineralogy, and they were mappable things that were created initially in 2006-07 from the drilling. So the main feature of that about the domains is that it's dominantly quartz in the north, it's carbonate in the south, and there's an overprint of that of chalcedony marcasite, the orange, and above the chalcedony marcasite is the silica sinter. Right. So there's early quartz veins grading to manganocarbonate veins overprinted by chalcedony marcasite that's linked to sinter above. They're mappable zones and important in grade control. We go to the next slide. This shows where the grade is best. So where the chalcedony marcasite zone overprints the quartz veins and the manganocarbonate zones, that's where it's 10 to 100 grams. You can see in the grade diagram above. Okay. Where you go out into the carbonate, the grade progressively drops off from that central zone out to the edge of the manganocarbonate where it's down to less than a ppm. Okay, so there's an overall grade zoning over the 1,200 metre length of the ore body, with the best grade where the zones all seem to overlap together. Okay, next slide. These are the domains as originally described and what sort of they're called now, or partly what I called them. The most distinctive thing and the characteristic thing at FDN is the beautiful banded manganocalcite veins that have chalcedony and have all the visible gold. You can see the top left picture and the left-hand side there is that high-grade sample I had in the webinar. The second zone is called FDN2, is the next to that. That is chalcedony with marcasite. In the right hand of those two pictures there, you can see that the chalcedony is brecciated. It's partly recrystallized, which is the whiter parts of it, and it's infilled with all that banded marcasite that's partly inverting to pyrite. Okay, that's characteristic of that significant zone that runs along the western side of the ore body for quite a long way. FDN3 in this model is the sinter and the underlying material. So the sinter sits on top some sediments and some outflow of breccia from the breccia pipe that it sits on. And within that, there's, as you can see in the right-hand picture there, the selatonite, which is that, here it looks kind of grey-green, but I'll show you other examples that are sea green, and they have free gold in with that selatonite. But the sinter is essentially made up of chalcedony with the selatonite. On the right-hand side, you see the quartz chalcedony veins. So in this one, a lot of the brighter white-coloured stuff is the crystalline quartz, whereas the less coloured at the top there, that's the chalcedony, and you can see that has sulfide ganguro bands in it as well. So the distinctive thing about this zone is that it's quite low, relatively low sulfide and quite high gold. In the FDN2, the gold is quite hard to see, and in the manganocalcite, it's good to see, and it's easy to see, and there's beautiful textures. Okay, so that was what existed in 2006-07, that kind of idea. We go to the next slide. This is the diagram that I drew by interpreting more of the textures and the mineralogy from those domains. So this is a section looking north. So the western side of the coloured zone in the diagram is the Graben fault, and the right-hand side of that blue zone is another Graben fault, and between the light blue and the green is another Graben fault. So the whole thing is forming while the Graben is developing and the centre is falling down. So the colours, the simplest view of the colours there is on the red on the top. Is the red there? That is the sinter with the selatonite and chalcedony that has free gold. You can see in the table on the right-hand side where it says domain length and gold ppm, they're the average grade of those zones in the whole 107 that goes through the whole thing. So that selatonite chalcedony zone actually has 16 metres at 11 grams in it. So it's well mineralized too. The blue zone there is the chalcedony marcasite, the stuff that has that nice fibrous and bladed marcasite, and that zone has, that interval is 105 metres at 7.8 grams. The thing about that is that a lot of that gold is refractory, so it's not necessarily easy to get out of that ore. The light blue zone, that's the chalcedony with quartz and the free gold, and that has that's the chalcedony quartz is the CHCC there, which is 22 metres at 9 grams in that zone. Then there's two greens there. The lighter green that's close to the blue, they're the pretty manganocalcite veins, particularly where they also have chalcedony and the base metals, and they have that spectacular gold. So there's 58 metres of 110 grams through that light green manganocalcite zone. As you go away from where the manganocalcite has quite a lot of chalcedony with it into where there's only carbonate, the manganese drops off and you get more calcite, but you get base metals. So there's still banded veins, but not as well banded as those close. And eventually when you get to the outside of that zone where the green finishes down the hole, there's you end up with just with silver and base metals in that zone. So that's there's only a little bit in that hole, but it's 2.6 meters at 0.4 gold. Okay, so all of the zones have some gold, but it's zoned from refractory gold to free gold to carbonate gold to more and more silver. So there's a distinct horizontal or down to the right zoning there from the sinter and the marcasite to the quartz to the carbonate based metals. Okay, so very distinct pattern of zoning that's mappable in those holes. So we can go to the next one. So here's a series of photographs of each of those defined zones, so you get a feel for what they look like. So from our model, if I just look at that, what I do is I close my eyes, open my eyes. What do I see first? Crustiform banding, breccia. Oh, that pink one has got moss texture in it, and the one on the right's got all that spectacular gold in it. So this is crustiform and coliform banding with white, partly crystallized chalcedony, pink manganocalcite that has moss texture in some places, and some bits of, I think that in the left-hand one, there's sphalerite in the band. So there's ganguro bands that you can see actually in all of those samples. And in the second one in, that's the one that has all the free gold. So next to the black band on the right-hand side of that photo there, that's a line of gold crystals along that sulfide band. Okay, so crustiform, coliform, carbonate. Next one. Here, this is the quartz, chalcedony quartz zone. So starting from the left, there's quite good crustiform banding there between grey quartz and white, grey quartz and white chalcedony, with some ganguro bands, and within it there's quite a lot of internal textural variation, which is the recrystallization of the chalcedony. The second sample has cobaltinitrite staining that shows up adularia. I think you can see that that's moss to crystalline adularia. It doesn't have proper crystal shape, but it's subhedral, if you like. The third one has carbonate blades, and they're still carbonates in there, preserved in amongst grey chalcedony and fine sulfide. The next one has the nice crustiform banding with the manganocalcite, and there's chalcedony and quartz with beautiful band of gold in it. And the right-hand one is the bonanza sample, where you have all that gold with the quartz and chalcedony. Okay, so calcite dominant with nice bands with free gold, chalcedony and quartz, nice bands with adularia, blades, and free gold as well. Next one. This is the banded veins that have marcasite and chalcedony in them. So the second one in is maybe the easiest one to see. That's a bit of wall rock there, and then a grey quartz band, a sulfide band, and then banded recrystallized chalcedony. Okay, and in the middle that's crystalline quartz. Okay, the one on the left has nice marcasite in a sort of a breccia kind of form with grey chalcedony and white recrystallized chalcedony. And then the third sample has, it's a little bit hard to see, but that creamy coloured quartz there, yeah, that's moss textured chalcedony. Okay, and the one on the right, particularly, you can see the difference between the white and the grey. That's recrystallized chalcedony in the white, and the grey is crystalline quartz. So these are ones where you've got those recrystallization of chalcedony textures because they're in these crustiform, coliform banded veins where the fluid conditions are fluctuating quite wildly. Okay, these are very high grade veins. Okay, next one. This is the chalcedony marcasite zone where the chalcedony is massive, not banded, where it forms a network of veins through the through the altered andesite in the left-hand side. Forms that irregular sort of grey patches in the second slide that's both alteration and vein. And in the third one, it's a breccia. It's a breccia with clasts of breccia in a new rock flower kind of matrix with little bits of quartz and fragments of veins in it. So it's a polymicted hydrothermal breccia. And the fourth one is the bonanza one that I've shown a couple of times before. That is, this they're all pyrite, where the arrow is the pyrite that's recrystallized from the marcasite, which is the brown phase on the left-hand side. Go to the left and down from there, in there, yes. That's marcasite, that part there. So the marcasite is being recrystallized to pyrite, and that's the process I mentioned in the webinar. That is liberates the gold from the marcasite. Okay, next one. Here's the sinter. There's a whole tray of sinter with beautiful sinter banding, and you can see the cavities in it where it's been aerated or where there was organic matter in it. The picture on the right is a sort of brecciated sinter pebbles, so the sinter can be is erupted as a gel that crystallizes into a ball. And in the lower one, you can see sort of a fine version of that, where the banding and the organic matter and the little spheres of chalcedony are all intermixed. So if you look carefully at the silica here, it has no coherent texture, so it's equivalent of the chalcedony that's in the veins. It's just more aerated and slightly different crystal structure. But I think here, as I do at Waitapu, that the sinter is an extension of the chalcedony zone in the veining model. Okay, next slide. This is the seladonite that you get in the sinter and underneath the sinter in the sedimentary rocks, and also in the breccia. So here it's that sort of sea green, blue-green colour in with the chalcedony, and that's a vein cutting the chalcedony marcasite that has quite a lot of free gold in it. The seladonite veins themselves can have free gold, and that's what makes up that. I think that interval that had 11 grams in it included quite a lot of seladonite veins. The other two pictures are from other deposits, Kencana in Indonesia and Pajingo in Queensland, but they show the seladonite as alteration of the host rocks rather than vein fill. But that is a very good guide spatially to where there's mineralization. Seladonite and epithermals of minerals that indicate gold, I think seladonite is one of the best. Okay. Next slide, Stellan. Okay, so here's a sort of a quick summary of what we've seen compared with the idealized model. Okay, so we saw the crustiform coliform quartz with adularia, which is equivalent of the CCX zone, the lower crustiform coliform zone in the model. We saw a lot of predominance of chalcedony, but chalcedony in the crustiform coliform veins with manganese calcite and with moss textures, and progressively with base metals, and then progressively more marcasite with free gold. In the chalcedony marcasite zone, where the chalcedony was massive, that corresponds with the massive chalcedonic zone in the in the general model. And the seladonite with chalcedony is an extension of that into the Sinter zone. So what this means overall, I think if we go to the next slide, that we're only representing part of the overall Larry Buchanan model. So FDN only has the CCX, CCH and CHM zones in the model. It doesn't have the crystalline zone or the even though it has bladed carbonate, where there is bladed carbonate, it's in the banded veins, not in a zone by itself. And we haven't seen any crystalline carbonate there. Okay, but what it means is that the origin of the mineralization in relation to the low sulfidation model is that it is a result of boiling, because we get all the crustiform, coliform zones, and then of gas condensation where the gas has got right up close to surface in the chalcedony marcasite and in the at surface in the sinters. Okay, so next one. Okay, so this is the model that I ended up with. That central diagram is a model that I ended up with from my interpretation of the zoning and the distribution of the zones. The diagram on the right just shows that what we talked about initially, that is that the system developed while the graben was opening. That means the faults were active all through the process of ore formation, and even in the very last stage of the ore formation, you have veins that extend right up through the sedimentary rocks that overlie the sinter. So the most distinctive thing geologically that we haven't really touched on very well before, that's in the central model, is that all that grey area adjacent to the fault, that is hydrothermal breccia. Okay, I call it hydrothermal eruption breccia because it sits above the boiling zone. So where it says explosion point on that diagram, down below there where everything stops, that's the point where the boiling was initiated. And that breccia is what localizes all the marcasite chalcedony and has the hot pool and then the sinter adjacent to that. So the blue and the yellow things at surface are the hot pool that breccia formed and the sinter that formed adjacent to it. Beside that, in the grey are and there, yes, where it's grey, that's where there's quartz or chalcedony. Outside that, where it's white and orange, that's where it's mostly carbonates. Okay, so there's a zoning from the breccia with the marcasite to the quartz and chalcedony dominant veins out to the carbonate and base metal veins. And that means, as you can see above the diagram there, you go from arsenic with gold in the breccia to gold with a bit of arsenic where you have the marcasite type veins, to free gold in the quartz and carbonate veins, to more and more silver with the base metals. Okay, so the sequence of formation there from the overprinting relationships is that the quartz veins form first, and they graded outwards to the carbonate veins, and then they got overprinted by the other part of the red veins, which are the chalcedony marcasite banded veins that have the good gold. So the reason that the best gold is in that position where the arrow is now is where you've got all the different types together. You've got the quartz veins, the carbonate veins, overprinted by the chalcedony marcasite veins, and they all have mineralization. So the high-grade ore is in that area where essentially where the red and pink lines are. Yeah, so in that zone there. All right. So this is complicated. I think those things are all related based on the timing and relationships, but what happened is that the final event on that structure, possibly at the last phase of movement, was a hydrothermal eruption which destroyed some of the existing veins and then overprinted the veins that had already formed adjacent to the breccia with more veins and added more gold to that zone. Okay, if we go to the next slide. So if I compare that model for Fruta del Norte with the generalized model we have for hot spring, what are called hot spring epithermal deposits, where you have this combination of veins and breccias and sinters. It is fundamentally the sequence. So in the model on the right, the veins are mainly underneath where all the sort of dispersed veins in the main alteration are, and the explosion point is there where the breccia starts, and then you have the illite and then silica sort of alteration above that, with the hydrothermal eruption breccias cutting through those and up into the zone where the sinter is. So that we have all those components in the Fruta del Norte model. It's just because it formed during fault displacement. The veins don't sit underneath the breccia, they sit mainly beside it. Okay, so in comparison with the model that we had in the original part of the webinar, we do see some but not all of the components of that model, but the parts we do see relate to boiling, and the boiling can be demonstrated to originate on that fault. And the thing that's different from just having simple veins is that there's this hydrothermal breccia overprinting the veins as well. Okay, so that's my Fruta del Norte story and model. I haven't had any involvement seriously since 2009, but I do follow the publications and the press releases by London. So I've always been interested in following the history there. If we go to the next slide. So this is just sort of following up on where we started. That this is it's a hot spring model. In New Zealand, the Maori people use the hot springs for cooking their food, and then on the right there's a picture of the FDN accommodation part of the camp when I was there in 2007. The tents under the tin roof. The office was also made out of timber with black plastic sheeting on the outside. So it's a very interesting story you can hear from Steve Leary about the whole progression of development of the deposit, but it's amazing to me how fast that happened. Okay, that's it for that talk. If you've got some questions about that, I'm happy to answer them. Yep.